Welcome back, everyone. So today we're going to talk about exponents, exponential functions, logarithms, and logarithmic functions. And we're going to get more in depth with exponents and logarithms in the separate sections, but the primary purpose of this lecture is to talk about exponents, their graphs, logarithms, their graphs, and how to do basic equations with exponents and how to work with exponents in general. So let's get started. Now, to give you a quick reminder, an exponent is a number that tells you how many times to multiply a number by itself. So if I have an exponential expression like, say, 4 to the third, okay? In this exponential expression, the larger number is known as the base, and the smaller number is known as your exponent. Now, in an exponential expression, the exponent tells you how many times to multiply the base to itself. So 4 to the third power is the same as 4 times 4 times 4, which if you do the math, remember not to add the 3, but multiply the 3. 4 times 4 is 16, 16 times 4 is 64. Now, one key important point to remember is that the base of the exponent is the number or variable that is directly in front of the exponent. So, for example, the base of this exponent is 7. The base of this exponent is 1, not 1/3. And this is where a lot of students make mistakes for this one. The base for the third exponent is 9 and not -9. And that is a key thing to remember. If I want something else other than the number or variable in front of the exponent to be its base, I have to use parentheses. So, since there's no parentheses, the base of the exponent is 4. However, here, in this example, since there's parentheses involved, the base of the exponent is -9, okay? So in this case, the base of the exponent is 9, and here the base of the exponent is -9. Now, why is this important? Well, whenever you raise a negative number to an even exponent, the negative goes away. So for example, in this case, the base is -2, and I'm asked to multiply -2 to itself 4 times. And if I do the arithmetic, I get -2 times -2 is +4. +4 times -2 is -8. -8 times -2 is +16. So whenever you raise a negative exponent to an negative base to an even exponent, the negative goes away, okay? Because remember, when you multiply negative numbers an even number of times, the negative goes away. So, some examples. -2 to the third power is -2 times -2 times -2, which is -8. -2 times -2 is +4. +4 times -2 is -8. And that makes sense because I'm raising a negative base to an odd exponent, okay? So if I have a negative base and even exponent, I get a positive result. Likewise, if I have a negative base and an odd exponent, I get a negative result. So negative base to an even exponent is a positive result. Negative base to an odd exponent is a negative result. Now, a couple of other things to remember about about bases and exponents. Let's take, for example, a situation like this. 4a in parentheses cubed. So in this case, since there's parentheses involved, the base is 4a, okay? So this is 4a times 4a times 4a, which means if you do the math, you get 4 cubed a cubed, or another way of saying this is 64a cubed. So how did what happened with this exponent? So if you have an exponent, if you have a base with multiple things being multiplied together, you can distribute the exponent to everything being multiplied. So when you have an expression, when you have two or more things multiplied together raised to the same exponent, you can distribute, and I hate using that word, you can distribute the exponent to everything being multiplied, which gives me, in this case, 64a cubed. And remember, this is known as the power of a product. Okay. Now, another property of exponents is the product rule, which says that if I have two exponential expressions being multiplied together, both with the same base, I can add the exponents. Okay. This is known as the product rule of exponents. The next property of exponents is known as the power rule. And the power rule says that if I have an exponential expression raised to an exponent, so in this case, the base of the outside exponent is a to the fourth, I can multiply my exponents. Okay, so product rule says if I have two exponential expressions multiplied together with the same base, I can add their exponents. Power rule says that if I have an exponential raised to an exponent, I can multiply the exponents. Okay, so it's key to remember or keep separate in your mind when to add the exponents and when to multiply the exponents. And the last thing we covered was the power of a product, which says that if I have two or more things multiplied together, all of it raised to the same exponent, I can distribute the exponent to everything being multiplied. Now, one thing to remember about when you distribute exponents. In this case, this would be 7 cubed p cubed, and then you can find out what 7 cubed is. But you cannot do this. Okay, you cannot distribute when you're adding bases. Okay, so this does not equal 7 cubed plus p cubed. Okay, so you can only distribute the exponent when the bases are being multiplied. Okay, you cannot distribute if it's being added or subtracted. And this makes sense because remember, when you square a binomial, you get a squared plus 2ab plus b squared. You do not get just a squared plus b squared. Okay, so this is another way of remembering that you can only distribute the exponent when the bases are being multiplied, not when the bases are being added. Now, what about fractions? How does exponents work with fractions? Well, having a hard time erasing here. Just want to erase. Okay. If I have an exponential expression divided by an exponential expression, both with the same base, then I can subtract the exponents. This is known as the quotient rule. Okay. Now, here I have a fraction. The whole fraction is the base of that exponent. So if I have this situation, I can distribute again the exponent to both the numerator and denominator. And this is known as the power of a quotient rule. So quotient rule says if I have an exponential divided by another exponential, bases are the same, I can subtract the exponents. The power of a quotient says that if I have a fraction, the whole thing being the base of an exponent, I can distribute that exponent to both the numerator and denominator. Now, two more other properties of exponents that are pretty important. Anything raised to the 0 exponent is 1. Anything raised to the 0 exponent is 1. And anything raised to the negative exponent is basically the reciprocal. Okay. So for example, 2/7 to the -3 is the same as 7/2 cubed. So whenever you have a negative exponent, to get rid of the exponent, to get rid of the negative, you can take the reciprocal of the base. Okay. So a to the -n, to get rid of the negative, we take the reciprocal of the base, which is 1 over a to the n, and then the power of the quotient says that this is 1 to the n, a to the n, which is 1 over a to the n. Okay, because 1 to any power is just 1. Now, a couple of naming things that we're going to talk about. Whenever we raise something to the power of 2, we say we are going to square it, or squared. Okay. Anything to the power of 3 is called cube or cubed. Okay. All right. Now, what about fraction exponents? Well, if you're doing fraction exponents like 1/2, 16 to the 1/2 power is the same as the square root of 16. Okay. So raising anything to a fractional exponent, you're basically taking the nth root of that base. So for example, 8 to the 1/3 power is the cube root of 8, which is in this case 2. All right. Okay, so this is basically the summary of all of the power of the properties of exponents. I would highly recommend that you put this in your notebook and practice with it, because going forward, we're going to utilize these extensively. So the next topic we're going to be talking about is exponential graphs, okay? Exponential functions and their graphs. So up to now, we've been dealing with two types of functions. We've been dealing with polynomials, and we've been dealing with rationals. And rationals can be thought of as the larger, broader category because we talked about polynomials being a type of rational. Rational functions being any function that can be written as a fraction, of which polynomials can. So the other type of functions that we deal with in mathematics are called transcendental functions. Transcendental functions. So they're either polynomial type in nature or transcendental type in nature. And the two types of transcendental functions that we tend to deal with are exponential or logarithmic functions, which are the same exact thing, or trigonometric or trigonometry functions. So an exponential function is defined as f of x equals a to the x, where a is the base and x is the exponent, and a is a number. So this differs from a polynomial because remember, a polynomial was anything like this: an x to the n plus a n minus 1 x to the n minus 1 plus dot 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 all the way to a to the 0. So that was polynomial. So the difference between a polynomial and an exponential is that in a polynomial, let's just simplify the polynomial like this. Call this. And the exponential function being g of x is a to the x. In a polynomial function, we're changing the base of the exponential expression. Okay, so the exponent stays constant, stays the same, and when we input a number for x, we're replacing the base of that exponent. In an exponential function, the difference is that we're not changing the base. The base will stay the same, but when we plug in a value for x, we're going to replace the exponent with that value of x. So the exponent changes. So another way of saying this is, in a polynomial, you'd have something like x squared, whereas in an exponential, you'll have 2 to the x. So as you can see, in the first type of equation or first type of function, when I plug in a value for x, what it does is it replaces the base of the exponential expression. So the base constantly changes. Whereas in the second, when I plug in a value for x, I'm changing the exponent, and the exponent keeps changing. Now, we talked about extensively the graphs of an exponential function, of a polynomial function, and we talked about the characteristics and how to find the zeros of a polynomial, etc., in the last chapter. So now we're going to be talking about the graph of an exponential function. Okay, the graph of an exponential function. And there's two types of graphs when we talk about exponentials. Either we have exponential growth or ascending functions, or exponential decay or descending functions. So this is exponential growth. And this is exponential decay. And we're going to talk about how to look at an equation and determine whether it's a growth or decay function. Now, remember we were talking about the properties of exponents, and what did I say was anything raised to the 0 power? Well, remember, anything raised to the 0 power is 1. So almost all exponential functions have a y-intercept at 0, 1. And the reason is because if I have an exponential expression like 2 to the x, if I plug in 0 for x, I get 2 to the 0, which is 1. If I have an exponential expression like this, 4 to the x, and x is 0, then 4 to the 0 is 1. So all basic forms of exponential functions have a y-intercept at 0, 1, or it crosses the y-axis at 1. Okay. Now, let's look at some other characteristics of exponential functions. So let's work with the easier one. F of x equals 2 to the x. Okay. So when x is 0, we said y is 1. So that means my y-intercept is at 0, 1. Now, let's do a t-table. If you remember from high school how to do a t-table, you draw a chart. There we go. So let's pick a couple of values. Let's pick 1, 2, 3, 4, and then 10. And you may need to use your calculator to figure this out, okay? So when x is 1, what happens? Well, we get 2 to the 1, which is 2, okay? Now, when we replace x with 2, we get 2 squared, which is 4. When x is 3, we get 8, so that's 2 cubed is 8. When x is 4, we get 16, because that's 2 to the 4th power. And if you do the math, at x equals 10, we get 1024, which is what 2 to the 10th power is. So that's pretty significant, okay? So if we plotted these points, 1, 2, 2, 4, 1, 2, 1, 2, 2, 4, 3, 8, 4, 16, we get a picture that emerges, okay? And let's look at how it looks. So when x is 0, y is 1, okay? When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. X is 4, y is 16. So what type of graph are we getting to the right of the y-axis? We get this curve that shoots up like this. Okay. And that's pretty significant because what does this say? That means that when x is 10, y is 1024. So that's pretty important to think. By just moving 10 spots on the x-axis, I have to go up 1024 spots on the y-axis to be able to plot this point. So in 10 movements on the x-axis, this graph shoots up 1024 spaces on the y-axis. And this is why exponential functions are pretty important, because in mathematics, exponential functions are the fastest growing functions that we have, okay? And they get very large very quickly. Now, let's see what happens when we go the other way, okay? When we go the other way. So let's see what happens when I plug in -1 for x, -2 for x, -3 for x, -4 for x, all the way to -10. Well, when I replace the x with -1, I get 2 to the -1, which is, remember how to deal with negative exponents. We make the base into, we take the reciprocal of the base. So 2 to the -1 is 1/2. 2 to the -2, we take the reciprocal, which is 1/2 squared, or 1/4. 2 to the -3 is 1/2 cubed, or 2 to the 1/8. So 1/2 cubed, which is 1/8. 2 to the -4 is 1/2 to the 4th, which is 1/16. And if we keep doing this, 2 to the -10 is actually 1/2 to the 10, which is 1/1024. Okay. So notice when we go to the left of the y-axis, so as x gets more and more negative, what does my y get closer to? If you notice, it keeps getting smaller, 1/2, then 1/4, and 1/8, and 1/16, and it keeps getting smaller and smaller and smaller. So it keeps getting closer and closer to 0, okay? Well, when is y 0? Well, when is y 0? Well, remember when y is 0, where are you? What line are you on? When y is 0, you're on the x-axis. Okay. So as my x keeps getting more and more negative, my y gets closer and closer, smaller and smaller, and gets closer and closer to 0. So the graph gets closer and closer to the x-axis. Okay. Will it ever get to the x-axis? Will y ever be 0? So the question is there some value that I can plug in for x so that my output is 0? And the answer is no. There is no value of x that I can plug in that gives me a 0. So what does that mean? Well, as x goes to negative infinity, or more and more negative, my output, f of x, approaches a number, 0. So you remember from our previous discussion in rational functions, we talked about as x goes to negative infinity, f of x approaching a number, in this case 0, that is known as a horizontal asymptote. So all exponential functions, the graph of all exponential functions have a natural horizontal asymptote, okay? A horizontal asymptote at the x-axis or y equals 0. Okay, so that means they'll get closer and closer to that line to the left of the y-axis, but it will never touch the x-axis at all. Okay, so once you go to the left of this y-axis, the graph will get closer and closer, inch closer and closer towards the x-axis or y equals 0, but it will never get there. So that's the definition of the horizontal asymptote. And that is a key hallmark characteristic of all exponential functions. The graph of all exponential functions have a horizontal asymptote, and usually at the x-axis or the equation y equals 0. So this graph right here is the graph of most exponential functions, most basic exponential functions. Okay, this shape or this picture of this graph resembles all basic exponential functions. Now we talked about a chapter or so ago about transformations, okay? So we talked about adding a number on the inside and what it happens, and adding a number to the outside and what happens to the graph. So remember, when we add a number to the inside of a graph or subtract a number from the inside, it shifts it left or right. And when we add or subtract a number on the outside, it shifts the graph up or down. Now, this is also true for exponential functions. So if I have an equation, f of x equals 2 to the x minus 3, that means it's going to be the same graph as this, but it's going to shift to the right. Remember, when I subtract, I'm making it more positive, so I'm going to shift the graph to 3 units to the right. Likewise, if I have a graph, an equation 2 to the x plus 3, this is going to shift it 3 units to the left. Okay. Now, when I add a number to the outside, so for example, if I have 2 to the x plus 7, this is going to shift it up 7 units on the y-axis. Okay. And if you subtract from the outside, it's going to shift it down 7 units. okay, down 7 units. Now, the key thing to remember is this. Since all exponential functions have a horizontal asymptote, whenever you shift the graph up or down, you also shift the horizontal asymptote. Okay, so if you remember, the graph of 2 to the x has a horizontal asymptote at y equals 0. And since this graph is shifted 7 units up, that means my horizontal asymptote shifts 7 units up. So instead of having a horizontal asymptote at y equals 0, it has the horizontal asymptote at y equals 7. And likewise, if I shift it 7 units down, the horizontal asymptote also shifts and down. So now the horizontal asymptote is y equals -7. Okay. Now, one thing we want to talk about is the transition point. This is unique for all exponential functions. So the transition point, if you look at this graph, the transition point is this point right here where things start shooting up really fast, okay? That's your transition point. Now, how do I calculate the transition point? So to calculate the transition point of an exponential function, so let's take, for example, 3 to the x plus 2, okay? To calculate the transition point, I make my exponent equal 0. So for example, in this case right here, I have to make x plus 2 equal to 0 and solve. So the transition point occurs when x is -2, okay? Now to find the actual point, you plug in -2 into the equation. So in this case, for this graph, the transition point will be at -2, 1, okay? So to find the transition point, make the exponent equal to 0 and solve. So that'll give you the x coordinate of the transition point. To find the y coordinate of the transition point, whatever you get for x, plug it into the equation. So let's do another example. Okay. So what would be the transition point here? I would recommend that you pause the video and try to do it yourself and then come back and see the work through. All right. So in order to make the transition point, to find the transition point, I got to take this exponent and make it equal to 0. Okay. So in order for the exponent to be 0, x has to be -3. And that means the x coordinate of my transition point is -3. And the y coordinate would be g at -3, which is -1. Okay, let's do another one. Calculate the transition point. Okay. So pause the video, try to do it, and then come back and see how we worked it. All right. So to find the x coordinate of the transition point, I take my exponent and try and make it equal 0 and solve. So the transition point will occur when x is 3. Well, what is the y coordinate when x is 3? So when x is 3, y becomes 3 as well, because 3 minus 3 is 0, and 5 to the 0 is 1. 1 plus 2 is 3. So the transition point is 3, 3. Okay. So some key things to know. So for an exponential graph, okay, the y-intercept, to find the y-intercept, set x equal to 0, okay, and solve. To find the transition point, to find the transition point, make the exponent equal to 0, find x, then find y, or x of x. Okay. The next thing you need to know is how to find the horizontal asymptote. So the horizontal asymptote is always y equals 0, which is the x-axis, unless you have something added or subtracted to the outside. If you have anything added or subtracted to the outside, remember you're shifting the graph up if you're adding, down if you're subtracting. So however many units you're shifting the graph up or down is your new horizontal asymptote. Okay. So let's look at a simple graph and graph all of the characteristics. Okay. So first thing we're going to do is find the y-intercept. Okay, so to find the y-intercept, you set x equal to 0. So two to the 0 minus 4 plus 3. Okay, 0 minus 4 is 2 to the negative 4 plus 3. Now remember, how do we deal with 2 to the negative 4? How do I make that negative exponent positive? So I take the reciprocal of the base. So it's 1/2 to the 4th power, which is 1/16, plus 3, which is approximately 3 and 1/16. Or if you have, if you want a improper fraction, it would be 49/16. So the y-intercept is at 0, 3 and 1/16. Now, next thing we want to find is the transition point. Okay, the transition point. To find the transition point, I want to set the entire exponent equal to 0. So x minus 4 equals 0. So When I solve, I get x equals 4. That means the transition point occurs when x is 4. Well, what is the y-coordinate of the transition point? I know the x-coordinate is 4. What is the y-coordinate? Well, to do that, I plug 4 back in. So the transition point occurs at 4, 4. Okay. Now, the next thing we want to do is determine the horizontal asymptote. So remember, the horizontal asymptote is normally y equals 0, unless I have something added or subtracted to the outside. Well, what do I have added or subtracted to the outside? I have 3. So the horizontal asymptote is y equals 3. So if I drew a graph of this, and it doesn't have to be exact, but if I drew a graph, I would say, okay, I would graph my y-intercept at 0 and 3 and 1/16. So 0, 3, 1/16. Okay. I graph my transition point. That's the point where things start rising really fast. So that occurs at 4, 4. And then I'd say my my horizontal asymptote is at y equals 3. Okay. And then I draw. So from the transition point onwards, it's going to shoot up pretty fast. Then to the left of the transition point, it's going to get closer and closer to my asymptote. And this will be the graph of 2 to the x minus 4 plus 3. Okay, now, a couple other things. Domain and range. Domain and range. So the domain, your collection of inputs or your x values for all exponential functions is all real numbers, always. So the domain for any of my exponential functions is all real numbers. Now the range, well, how do I look at a graph and determine its range? So the range will be basically from your asymptote all the way to infinity, okay? It'll be from the asymptote all the way to infinity. So the asymptote is at 3. So my asymptote will be, my asymptote is at 3, so my range is from 3 to infinity. Now, the reason I'm using parentheses around 3 is because, remember, this is an asymptote. The graph will get really close to the asymptote, but it will never touch it or ever cross it. So because of that, to indicate something that can get really close but not be at that number, we have to use parentheses. So here's another example. So here's an exponential function, and I want to know the y-intercept, the transition point, the asymptote, and the domain and range. Well, this thing has something unique to it. It has 3 being multiplied to my exponential expression. So 3 is separate from this entire exponential expression. The exponent, remember, only deals with the number or variable directly in front of it. So the exponent only pertains to 2. And 3 is going to be multiplied to whatever I get as my result out of that result. So let's see what happens. Let's see what effect 3 has to this whole thing. So let's begin first by finding the y-intercept. And as I do each step, I recommend that you pause and try to do all of this by yourself and then come back and see how we do the solutions. So to find the y-intercept, remember we said x equal to 0. So we get 3 times 2 to the 0 plus 2 minus 1. So 3 times 2 squared, because 0 plus 2 is 2, minus 1. So remember your order of operations. You do exponents, then multiplication, then addition and subtraction. So the first thing we're going to do is the exponent. So 2 squared is 4. Then we're going to multiply 3 times 4, which is 12, minus 1, which is 11. So my y-intercept is at 0, 11. Okay. Now, next thing we're going to do is find the transition point. This is where the graph shoots up almost vertically. Okay. So remember, to find the transition point, I have to set my entire exponent equal to 0 and solve to get the x-coordinate of the transition point. So the transition point occurs when x is -2. And in order to find the y-coordinate, I go back and plug it in again. So -2 plus 2 is 0. So remember exponents first, so 2 to the 0 is 1. 3 times 1 is 3, minus 1, which gives me 2. So the transition point for this graph occurs at -2, 2. So you see the effect the number 3, this number 3 has on this entire graph. It changes the y-intercept, and it also has an effect on the transition point. Now, the horizontal asymptote, remember, is y equals 0 unless something is being added or subtracted. But in this case, -1 is being subtracted. So that means the graph is being shifted 1 unit down. That means my y-intercept is y equals -1. Okay. Domain for all exponentials is the same. It's all real numbers. And the range is basically from your your horizontal asymptote, which is -1, all the way to infinity. Okay, so what happens if my exponent is negative, like in this case, y equals a to the -x? Well, remember, if we have something like when we have a negative exponent, how do we make the negative exponent positive? We take the base and do the reciprocal. So the reciprocal of 2 is 1/2. So this is the same as 1/2 to the x power. Okay. So if your exponent is negative, or if your base is a fraction or less than 1, okay? So if the base is less than 1, or if your exponent is negative, this is known as exponential decay. Now, let's do a chart. Let's see what happens as I go to the right of the y-axis. So as my x gets more and more or larger. So when x is 0, 2 to the -0, which still, there's no such thing as a -0, it's still 0. So 2 to the 0 is still 1, okay? Now, when x is 1, it becomes 2 to the -1, which is 1/2. When x is 2, that's 2 to the -2, which is 1/4. When x is 3, it's 2 to the -3, which is 1/8, and so on and so forth. So notice, as x gets larger and larger when the exponent is negative, my y, my output gets smaller and smaller, gets closer and closer to 0. Okay. Now, what happens when I go in the opposite direction? So I go more left or I go more negative. Okay. So when x is -1, that's minus -1, which makes it positive. So that's 2 to the 1, which is 2. When x is -3, I get 2 to the minus -3, which is 2 cubed, which is 8. And if you see, as I get more and more negative, I get larger and larger. Okay. And the same thing happens if the base is a fraction. So for example, 1/2 to the -1, remember, 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2, say, to the 4th is 1/16. And if I go more negative, 1/2 to the -1 is the reciprocal of 1/2, which is 2. 1/2 to the -3 is the reciprocal of 1/2, which is 2. 2 cubed is 8. So in these cases, when either the exponent is negative or if my base is a fraction, less than 1, the graph gets larger and larger when x becomes more and more negative, but gets smaller and smaller and approaches the x-axis or 0 as x gets larger. So as x gets larger or more positive, y gets smaller and smaller. And as x gets more and more negative or goes to negative infinity, y gets larger and larger. So this is the graph of an exponential decay. Okay, and this is the graph that results when either the exponent is negative or the base is a fraction, So this graph is the graph of 4 to the -x, or the graph of 1/4 to the x. And this line that's to the left of this, so this guy right here is the graph of 2 to the -x, or the graph of y equals 1/2 x. The other characteristic, so it's basically, if you look at it, it's like basically flipping the graph across the y-axis. So it's called decay because it keeps going smaller and smaller. And everything else still holds true. If you want the transition point, you have to solve for where the exponent is 0. If you want the y-intercept, you have to set the x equal to 0 and solve, and so on. Okay, the domain is still all real numbers. The range is from your asymptote all the way up to infinity. Now, the only other thing is the transition point. The transition point is, instead of in a growth function, to the right of the transition point, it'll go up. But in a decay function, the left of the transition point, things go up. Okay. So I would like you to practice doing the difference between 3 to the x and 3 to the -x. Okay. And I'd say pause, graph it, and then come back and see the plot. All right. So I'm going to graph 3 to the x using my pink line. So the y-intercept occurs when x is 0. So when x is 0, y is 1. So the y-intercept is at 0, 1. The horizontal asymptote is at y equals 0. Okay. The transition point is when the exponent is 0. So when x is 0, so it's the same as the y-intercept. So at 3 to the x, the graph looks like this. To the right of the transition point, it goes up. To the left, it gets closer and closer to the horizontal asymptote, which is y equals 0, or your x-axis. Y equals 3 to the negative x. Remember, how do I make my negative exponent positive? I can also take the reciprocal of the base. So 3 to the negative x, same characteristics, y-intercept and the transition point is the same at 0, 1. So it's the same as the previous graph. And I'm going to do this in blue. But since this is a decay, to the left of the transition point now, we're going to go up, and to the right, we're going to get closer and closer to my asymptote. The domain for both functions is still the same, all real numbers. And the range is from my horizontal asymptote, which is 0 to infinity. Okay, so hopefully this helps you understand exponential functions better and how to graph them. And I highly recommend you practice doing some of the graphs. In addition, I highly recommend that you review your properties of exponents, like the power of a product, the power of a quotient, and so on and so forth, because you're going to need to know how to do these, because the next section, the next lecture we're going to talk about is logarithms, which is basically the reverse of these things. And if you don't know how to deal with exponents and how to work with properties of exponents, then dealing with logarithms is going to be that much harder. If you have any questions, reach out to me, message me, and I will see you next time. Take care.